Your freestanding tent acts as an airfoil that generates over 15 kilos of lift in a gale, effectively turning your shelter into a kite without proper vector management. Structural integrity in backcountry shelters is primarily a function of pole intersection geometry. A pure tunnel tent relies on hoop tension, but a geodesic dome distributes wind load through triangulation, effectively minimizing the unsupported span length of any single pole section. The relationship between stability and weight is nonlinear. Doubling the pole intersections often quadruples the static load capacity. This rigidity prevents the fabric from deforming under snow load or wind pressure, which is critical for preserving your internal habitable volume. Marketing claims often tout freestanding designs, but physics dictates otherwise. As wind speed accelerates over the curved surface of a dome, Bernoulli's principle creates a low-pressure zone above the tent. Without stakes, even a heavy expedition tent becomes a tumbleweed. Guy lines aren't optional extras. They transfer horizontal wind shear into vertical compression on the poles. The optimal angle is 45 degrees. If the line is too vertical, you lose lateral holding power. Too horizontal, and the vector force pulls the stake straight out of the soil. This applies to tarps as well. High-end tarps utilize catenary curves, curved cuts in the ridgeline and edges. This ensures that tension applied at the corners distributes evenly across the entire fabric plane, preventing the flapping that eventually fatigues the waterproof coating. Speaking of coatings, waterproof is a marketing term. Hydrostatic Head, HH, is the engineering reality. A 1200 mm rating handles rain, but kneeling on a tent floor creates pressure spikes exceeding 5000 mm. If your bathtub floor is rated below 3000 mm, you are relying on surface tension, not the membrane. Single-wall tents fight a losing battle against thermodynamics. Unless the external vapor pressure is significantly lower than internal humidity, moisture will condense. Double walls mitigate this by pushing the dew point to the fly, keeping the phase change away from your sleeping bag. For bike packers, the equation changes. The drag coefficient of a handlebar roll determines your daily calorie burn. A bivy sack system removes the wind profile entirely, but requires managing condensation through airflow rather than insulation layers. This creates a distinct trade-off. A tarp plus bivy offers the highest protection to weight ratio, but demands complex site selection skills. A tent offers brain-off protection, but adds rotational weight to your steering or static weight to your seat post. Material choice also affects field performance. SilNylon absorbs water and sags, requiring retensioning at 2 a.m. SilPoly is hydrophobic and holds its pitch. The molecular structure of polyester resists stretch, maintaining that critical aerodynamic shape through a storm. Finally, consider soil mechanics. A stake's holding power is roughly proportional to the square of its depth. Driving a 6-inch stake only 3 inches deep creates a lever arm that magnifies the extraction force. Full insertion is a non-negotiable safety margin. Ultimately, a $2,000 Dyneema shelter pitched broadside to the wind will fail before a cheap tunnel tent pitched nose-in. Understanding aerodynamics and tension vectors is the only true survival gear you carry. Geometry beats budget. Learn to pitch for the conditions.